Hello everyone, my name is Batian Najanau, metric number 65550, and today I'm gonna explain to you all about 4 important technologies in remote sensing. Stay tuned. Before we going into the 4 important technologies in remote sensing, let me explain to you all about what is remote sensing. Okay, let us start now. Generally, remote sensing refers to the activities of recording, observing, and perceiving objects or events at faraway places. The sensor can be installed in airplane, satellite, or space shuttle to take pictures of the object or events on the Earth's surface. Therefore, the sensors are not in direct contact with the objects or the event being observed. The information needs a physical carrier to travel from the objects to the sensors through an intervening medium. The electromagnetic radiation is normally used as an information carrier in remote sensing. The output of a remote sensing system is usually an image representing the objects or the events that is being observed. Technically, in remote sensing system, the sensors can be divided into 2 types, which is the active and the passive sensors. So, the first technology that I'm going to talk about is electro-optical sensors. Satellite images are acquired by electro-optical sensors. Each sensor may consist of various amount of detectors. The detectors receive and measure reflected or emitted radiance from the ground as electrical signals and convert them into numerical values which are stored on board or transmitted to a receiving station on the ground. The incoming radiance is often directed toward different detectors so that the radiance within a specific range of wavelength can be recorded as a spectral band. The major type of scanning system used to acquire multi-spectral image data include across-track and along-track scanners. Instead of imaging a ground scene entirely in a given instant in time, a cross-track scanners scans the Earth's surface in a contiguous series of narrow strips by using a rotating mirror. These ground strips are oriented perpendicular to the flight path of the platform. As the platform moves forward, new ground strips are created. Successive ground strips build up a 2-dimensional image of the Earth's surface along the flight line. This technique is sometimes called Wishbone scanning, since the scanner whisks the Earth's surface as the platform advances along the flight direction. The incoming reflected or emitted radiation is frequently separated into several spectral bands, as these remote sensing scanning systems are capable of multi-spectral imaging. The near-ultraviolet, visible reflected IR and thermal IR radiation can all be used in a multi-spectral remote sensing system, which usually has 5 to 10 spectral bands. A set of electronic detectors, which is sensitive to a specific range of wavelength, detects and measures the incoming radiation for each spectral band and save as digital data. Across-track scanners generally have a wide image swath. Although their mechanical system is complex, their optical system is relatively simple. Across-track scanners have been widely used in the satellite remote sensing programs. Well-known examples include those scanners on board the Landsat Multispectral Scanner (MSS), Thematic Mapper (TM), and Enhanced TM Plus (ETM Plus). These sensors were the prime Earth observing sensor. So, next I'm going to talk about the thermal infrared sensors technologies. Thermal IR scanners are a special type of electro-optical sensors. The thermal scanners detect and measure the thermal IR portions of the electromagnetic radiation instead of visible near IR and reflected IR radiations. Because the atmospheric absorption is very strong in some portions of electromagnetic spectrum due to the existence of water vapor and carbon dioxide, thermal IR sensing is limited to two specific regions, from 3 to 5 UM and 8 to 14 UM, known as atmospheric windows. Comparing with the visible and reflected IR spectra, thermal IR radiation is much weaker, which require the thermal sensors to have large IFOV sufficient to detect the weak energy to make a reliable measurements. The spatial resolution of thermal IR channels is usually coarser than that for the visible and reflected IR bands. For example, the Landsat TM sensor has a spatial resolution of 120 m in its thermal IR band and 30 m in its visible through mid-IR bands. An advantage of thermal imaging is that images can be acquired at both day and night time, as long as the thermal radiation is continuously emitted from the terrain. Photo detectors sensitive to the direct contact of photons on the surface are used in the thermal sensors to detect emitted thermal IR radiation and are made from some combination of metallic materials. To sense thermal IR radiation in the 8 to 14 UM interval, the detector is usually an alloy of mercury, cadmium, tellurium. Mercury-doped germanium is also used for these thermal imaging windows, which is effective over a broader spectral range of 3 to 14 UM. Indium antimony is the alloy used in detector in the range of 3 to 5 UM. To maintain maximum sensitivity, these detectors must be cooled on board to keep the temperature between 30 and 77 K, depending on the detector type. In addition to the thermal detectors, the thermal scanners have two other basic components: an optomechanical scanning system and an image recording system. For cross-track scanners, an electrical motor is mounted underneath the aircraft with a rotating shaft oriented parallel to the aircraft fuselage, thus the flight direction. The total angular field of view typically ranges from 90 degrees to 120 degrees, depending on the type of sensors. The incoming thermal IR energy is focused from the scan mirror onto the detectors, which converts the radiant energies into an appropriate level of analog electrical signal. The resulting electrical signals are sequentially amplified and recorded on magnetic tapes or other device. These signals can be displayed in monitors and can be recorded and analyzed digitally after analog to digital conversions. For each scan, the detector's response must be calibrated to obtain a quantitative expression of radiant temperature. The third technology in remote sensing will be passive microwave and imaging radar sensors. The electromagnetic radiation in the microwave wavelength region 1 cm to 1 m in wavelength has been widely used in remote sensing of the Earth-land surface, atmosphere, and ocean. In comparison with visible, reflected, and thermal IR spectra, microwave has a longer wavelength. This property permits microwave to penetrate through clouds cover, haze, dust, and so on in the atmospheric while not being affected by atmospheric scatterings, which affect shorter optical wavelengths. The detection of microwave energy under almost all weathers and environmental conditions is especially important for tropical areas where large clouds covers occur frequently throughout the years. Passive microwave sensors operate in a similar manner as those for thermal IR imaging. These sensors are typically radiometers, which require large collection antennas, either fixed or movable. The passive microwave sensors detect and measure naturally emitted microwave energy within the field of view, with wavelength between 0.15 and 30 cm. The emitted energy is mainly controlled by the temperature and moisture properties of the emitting object or surface. Because the wavelengths are so long, this emitted energy is fairly small compared to optical wavelengths. As a result, the field of view for most passive microwave sensors are large to detect enough energy to record a signal, and the data acquired by such sensors are characterized by low spatial resolution. Passive microwave remote sensing using air and space-borne sensors has been used for several decades in the study of terrestrial system, meteorology, hydrology, and oceanography. Owing to microwave sensitivity to moisture content, passive microwave sensing is widely used for detecting soil moisture and temperature, as well as assessing snow melt conditions. In addition, microwave radiation from below thin soil cover provide helpful information about near-surface bedrock geology. On board some meteorological satellites, passive microwave sensors are the device used to measure atmospheric profiles, water and ozone content in the atmosphere, and to determine precipitation conditions. On ocean, passive microwave sensors track sea ice distribution and currents, and assess sea surface temperatures and surface wind. These sensors are also useful in monitoring pollutants in the oceans and in tracking oil slicks. And the fourth technology that I'm going to explain today is light detection and ranging. Light detection and ranging, or LiDAR, is a technology that dates back to the 1970s when airborne laser scanning systems were developed. Like radar, it is an active remote sensing technology. The first system was developed by NASA, and it's operated by emitting a laser pulse and precisely measuring its return time to calculate the range height by using the speed of light. Later, with the advent of GPS in the late 1980s and rapidly pulsing laser scanners, the necessary positioning accuracy and orientation parameters were achieved. The LiDAR system has now become comprehensive, typical with 4 primary components including a rapidly pulsing laser scanners, precise kinematic GPS positioning, inertial measurement unit for capturing the orientation parameter, i.e. tip, tilt, and roll angles, and a precise timing clock. With all the components, along with software and computer supports, assembled in a plane and by flying along a well-defined flight plan, LiDAR data are collected in forms of records of the return pulse range values and other parameters. After filtering noise and correcting, laser points coordinates are calculated, and a basic ASCII file of X, Y, and Z values for radar data is formed, which may be transformed into a local coordinate system. Since the inception of LiDAR system, LiDAR technology has been used widely in many geospatial applications owing to its high-resolution topographic data, short acquisition times, and reasonable cost compared with traditional methods. For example, LiDAR point clouds data show an excellent potential to identify tree shapes and height. So, let me conclude. Regardless of passive or active remote sensing system, all sensing system detects and record energy signals from the Earth's surface features and from the atmosphere. Data collected by this remote sensing system can be either in analog format, for example, hard copy aerial photography or video data, or in digital format such as a matrix of brightness values corresponded to the average radiance measured within an image pixels. The success of data collection from remotely sensed imagery require an understanding of 4 basic resolution characteristics, namely spatial, spectral, radiometric, and temporal resolution. That's all. Thank you for watching. Stay tuned for the next video.